the last session before lunch. This talk is about natural language processing, and in particular word embeddings, which are a family of algorithms that are getting a lot of attention in the last couple of years. A couple of words about myself. I am a data scientist based in London. Most of what I do nowadays is Python and text analytics. And a few years ago, I did also a lot of work in social media, so some of my efforts ended up in that book that you see on the right. And with my publisher also, we have been working on a video course for data analytics in Python, and it was released about 20 minutes ago, so this is kind of new. I've seen a few familiar faces in the audience, so maybe we met before at the PyData London meetup. In fact, I'm one of the organizers. PyData is at the intersection of Python and data science, and we have a nice meetup once a month, and our annual conference coming up actually next week. So word embeddings. This talk is really an introduction, so there will be some theory, but not too much. It's more about the kind of linguistic intuition behind word embeddings, what they are, what they look like, what we want from them. And then for the practical part at the end, there will be a little bit of example with Python. So terminology. Word embeddings are vectors that represent words. So what you see here, they are all synonyms. Word embeddings, word vectors, also semantic vectors sometimes, and distributed representation, because the meaning of a word is distributed across multiple dimensions. And why is this important? Well, in data mining, the way you represent your data is crucial for the success of your application. And in text mining, it's the same. So the way you represent your text is crucial for the success of your application. So word embeddings are really an interesting way to represent your text. And in terms of practical applications, anything related to NLP is a fair game, really. So I'm just mentioning a few examples of applications: classifications, recommender systems, search engines, so you type in your query and then the engine understands your query, machine translation, and then many, many more. So really anything about NLP can benefit from the use of word embeddings. And I want to start first with a couple of options to represent text before we build up towards word embedding. So the first option is called one-hot encoding, and this is quite common in many machine learning tasks or applications. So in one-hot encoding, you have vectors representing words, and they are called one-hot because only one bit is a hot at a time. So there is a single one, and then everything else is 0. And what we have here, you can see essentially one dimension per word. So each dimension is representing a single word in the vocabulary. And there are a couple of problems with this kind of representation. The first one is dimensionality. So we have many, many dimensions, as many as the words in our vocabulary. And the second problem is we don't really have a notion of similarity between these words because they don't have dimensions in common. The next representation is called a bag of words. This is quite common, quite popular. This is used to represent documents rather than words. And we still have vectors, so document vectors here. And we still have one dimension for each word, essentially. So in this example, in document 1, you have the word Rome coming up 32 times, the word Paris coming up 14 times, and so on. We still have a huge number of dimensions, but at least we have some notion of similarity because the different document vectors, they share some dimensions. And this is bringing us to the core topic of this talk, word embeddings. So what are word embeddings? Word embeddings are vectors, and the example is a bit made up just to showcase a couple of aspects of word embeddings. So they are vectors, and what do we want from them? We want the number of dimensions to be much smaller than before, so much smaller than the vocabulary size. And then we want to capture the meaning of our words and to capture some similarity between words. For example, Rome and Paris are somehow similar, so they're both cities, they're both in Europe, they're both capital, they're both nice places to visit. And we want the similarities to be captured by some of our dimensions, so you see the numbers in some dimensions are kind of similar. And also, Italy and France, they are similar concepts. They're both countries, they're both in Europe. The language is coming from Latin for both. The wine is good, and so on. So all these similarities, we want them to be captured in some other dimensions. One step further, Rome and Italy are also somehow similar. Rome is the capital of Italy, so we would like this particular semantic relationship to be captured by other dimensions. So if we put this in pictures, essentially Rome and Paris are close to each other because they're similar. Italy and France are also close to each other because they're similar. And then you almost see this direction, which is representing the relationship. Rome is capital of Italy and Paris is the capital of France. So essentially this is the kind of the magic with word embeddings. You can do vector arithmetics. So if you start with the vector for Paris, you add the vector for Italy, and then you remove the vector for France, you end up with a vector which is very, very similar to the vector for Rome. So we capture this analogy, essentially. We don't have vectors yet. We have language. So what's the main linguistic intuition behind word embeddings? The main linguistic intuition is called the distributional hypothesis. And this is nothing new. This is coming from the 50s. And every talk about word embeddings is referencing this particular citation. You shall know a word by the company it keeps, by John Firth, 1957. There's another one from a couple of years earlier. And this may be a little bit more clear. Words that occur in similar contexts tend to have similar meaning. So in summary, you can approximate the meaning of a word using the context around the word itself. This is the idea behind the distributional hypothesis, and this is what is used for word embeddings. So I give you an example here. You have a sentence, I enjoyed eating some pizza at the restaurant, and we focus on what's important, so that's our focus word, pizza. And everything else is the company it keeps. So you can use the company it keeps to represent the meaning of the word pizza. Pizza is something that we eat. Pizza is something that we have at the restaurant. Pizza is something that we enjoy. And then you scale it up to thousands of sentences, and once you aggregate the company it keeps, you have the deep, true meaning of the word pizza. Counterexample, 2 sentences. I enjoyed eating some pizza at the restaurant, and I enjoyed eating some pineapple. So these are our 2 different focus words, pizza and pineapple. And maybe you see where this is going. We have the same context. So essentially, according to what I told you so far, same context means same meaning, right? And well, of course, people have different opinions, but for me, this is outrageous. So we're just having a bit of fun here, but really it also opens for a discussion on data quality and maybe even ethics, right? So your language in general, will pick up all the cultural biases, and your models are going to pick up these biases as well. So your model is only going to be as good as your data. So if you have a bias in your language, in your data set, it's going to be reflected in the model itself. Okay, now for the theory, word embeddings are a family of algorithms, and I want to mention word2vec in particular, which is kind of a family within the family. And it was the first approach being widely successful. It was an academic success, and also they released the software open source, so it was kind of picked up by the community. This is coming from Google, so Thomas Mikolov and colleagues from Google a few years ago. They published a couple of papers, efficient estimation of word representations, vector space, and distributed representation of words, phrases, and the compositionality. And the concepts described in these 2 papers, they ended up in what we know today as word2vec. So how does it work? The goal is to learn vectors representing words. And when you look at things from a distance, maybe everything looks kind of the same. So the approach, without giving too much details yet, first we choose an objective function, you initialize randomly, and then you run stochastic gradient descent until you end up with your vectors. And if you've done some machine learning before, maybe you've seen the same approach applied in many different contexts. So from a distance, everything looks kind of the same. So maybe what's interesting here is what's going on with the objective function. So back to our pizza example. Pizza is our focus word, and everything else is the context. In terms of objective, what we want to do here is we want to maximize the likelihood of the context given the focus word. In other words, we are going to end up with a bunch of probabilities that look like this. So probability of observing the context word given the focus word. And back to the example with a bit more details. So we have our our focus word here, pizza, and we want to iterate over all the context words. So we start from the beginning of the sentence. We see the word I, given that the focus word is pizza, so we bump up the probability of I given pizza, and then we move on. We see enjoyed given pizza, and we bump up the probability. We see eating given pizza, we bump up the probability. And then we do the same and the same for all the words until the end of the sentence. Once we reach the end of the sentence, we move on to the next focus word, and we repeat the process again. So we see the word I given at, and you bump up the probability. You see enjoyed given up, and you bump up the probability, and you see where this is going essentially. We have two nested for loops, if you want, and then the heart of the matter is bumping up these probabilities. I keep saying bumping up the probabilities, but what's the probability of eating pizza? We haven't defined it yet, so there are a couple of question marks here. So we call the focus word, pizza in this case, our input, and we call the context word our output. Ideally, we would like the probabilities to be dependent on the vectors. We are learning vectors, so we can rewrite the probability in terms of vectors. And using this notion of input and output, we can generalize, so we are just rephrasing things. And we're talking about the probability of the output vector given the input vector. So that's the general case, and we still haven't defined the probability. So with this vector probability, ideally we would like the probability to be high when the vectors are similar. So one idea is, why don't we use a notion of vector similarity, for example, cosine similarity, quite common and quite easy to understand. The problem with cosine similarity is that it's not a probability. It's a number between -1 and 1. So the next idea is, let's take cosine similarity and let's throw it into a softmax function. The softmax function gives you a number between 0 and 1, so it looks like a probability, and it also has a probabilistic interpretation. So essentially, the softmax of the cosine is our probability itself. So the softmax is essentially the exponential of the cosine normalized over the sum of all the exponentials across the vocabulary. And if you've done some machine learning before, maybe you've seen already softmax, cosine, and whatnot. If this is new for you, maybe it looks like a big scary formula, but you don't have to focus on the details here. Just look at things from a distance. So the overall idea, what we've done so far with this algorithm in terms of learning vectors, we've been learning word vectors using stochastic gradient descent on the softmax probability. So that's the overall idea of the word-to-vec algorithm. And here you have all the keywords, all the ingredients, if you want to dig into details. If the theory is not enough so far, there's more. There's a follow-up work, also from Google. It turns out you can learn vectors that represent not only words, but also sentences and documents. This is called paragraph vector in that paper, and as a reference to word-to-vec is also called doc-to-vec. And we have basically the same notion, and our probability only has an additional component at the end, the label that you see as extra condition. The label is basically a sentence ID, document ID, whatever you like ID, to group the probability for sentences, paragraphs, documents, or whatever you like. Anyway, the approach is essentially the same. So Word2Vec was really popular because it was an academic success on one side. The word representations are really good. And on the other side, they also released the software as open source. So there is a tool written in C, released by Google, so you can download it and use it to train your vectors. And they also did the training on a corpus of Google News, so billions of words essentially, and they released the vectors in binary form. So you can even download these vectors and essentially kill the training time for your application. Anyway, I focus on Python. So for the Python side, there's a library called GenSim. The tagline for them is topic modeling for humans. So they implement a lot of different algorithms for NLP, and they stick a nice and easy to use interface on top of it. So it's really, really easy to use. And GenSim became very, very popular because when they released the Word2Vec implementation for Python, it ended up being faster than the original C implementation from Google, because there is some crazy optimization using NumPy and Cython and little tricks going on under the hood. But the interface is pure Python for you as a developer, as a user. So pip install GenSim, or if you prefer, conda install GenSim, and then you are good to go. And I want to give you a couple of examples for applications of word vectors. So this is some work that I did with a former client of mine. They have a platform for recruitment, so essentially you upload your CV on one side, and then companies upload job specs on the other side, and in the middle, the machine learning platform does some matching to put the right people on the right job. And we did a pilot to see if word embeddings can be useful here. So we had a bunch of CVs. Each CV has a bunch of experiences, and each experience has a bunch of skills. So we ended up with a vocabulary of about 15,000 unique skills. A little bit of code is relatively straightforward. So you import the Word2Vec class, then we have our data somewhere in JSON format, CSV format, doesn't really matter. Then the custom part is the third line, the corpus reader. So depending on the format of your data, you need to read them, and then you can, this is a Python generator actually, you can yield one experience at a time, so you don't need to load the whole corpus in memory. And then you feed it to the Word2Vec class. And for the Word2Vec class, there are also a few optional arguments that I'm kind of hiding here, but you can personalize the number of dimensions, the size of the context, and so on. So after you train your model, you end up with a bunch of vectors representing words. So this is the vectors for the word chef, and we look at the most similar words. So chef is very similar to cook. In fact, they are synonyms. And then we also notice that the vector for chef is very similar to other vectors, for example, bartender or waitress. They're not really synonyms, but they all kind of belong together because they're all part of the restaurant business or food industry and so on. So that's quite interesting, and it makes sense. Now, the word chef also has a different meaning. If you are a DevOps engineer, maybe chef is one of the tools that you use. So this is the nice thing with word vectors. You take the vector for chef, and then you remove the vector for food, and you end up with a vector that is very, very similar to Puppet, Ansible, Salt, and these are all tools in the DevOps space. So clearly, the model picks up on this aspect of the language and on how it's used in our data. So that was really interesting. And we found it particularly useful in the early stages for the exploratory phase of our project. So exploring and understanding our data was really an interesting step here, because it's when word embeddings were really, really useful. And also in terms of applications for query expansion, query suggestion, and the recommendation system in general, we managed to apply word embeddings. I'll give you another example on a lighter note. This is kind of a side project of mine. I like beer, and I like data, and I like Python, so I thought, why not putting everything together? And I took this data set of beer reviews, about 3 million documents, and all the different beers are categorized according to styles. So there are 89 different styles, and then you see the numbers. There's a lot of words in this particular data set. And for this example, I'm showcasing doc2vec rather than word2vec. But it looks very similar. So you import the class, you have your data somewhere, and you write your custom corpus reader. Because doc2vec also requires the label to be there, the corpus reader will yield one review at a time together with the beer style. So the beer style is our sentence ID or document ID. And then again, you feed it to the doc2vec model. Now, this one was about 1 gigabyte of data. So there's a bit of pre-processing and the training time as well. So remember to serialize your data and save it to disk. If I'm mentioning this, you know that it took me 7 hours rather than 3.5. I forgot to pickle the first time. So we have document vectors rather than word vectors. So here we pick the vector representing the beer style stout. It's a style of dark beer. And we look at the other similar vectors. And if you know about beers, you see, this makes sense. So we have other versions of stout. We have porter, which is also dark beer. And if you go down the list, you will end up with beers that are a bit different, but still on the kind of dark side. When you train the doc2vec model, you also have the word vectors anyway. So you can see what are the words that are mostly used to describe a particular document. Our document is, again, stout in this case. And you see the words that are mostly used are coffee, espresso, charcoal. This is kind of the aroma that you expect in this particular style of beer. And there's a counterexample. If you go for a wheat beer, which is more kind of refreshing, you have lemony, orangey, zesty notes, and so on. So all these words are the ones that are used to describe this particular style of beer. And again, it all makes sense. Now, given the word vectors and the document vectors, you could take them and, because the vectors have 200-300 dimensions, so how do you visualize them? You can do some dimensionality reduction here using principal component analysis, PCA. So take the vectors, throw them into a PCA, and the output is a two-dimensional kind of thing that you can visualize easily. And what's going on here is we don't really have a clear clustering of different beer styles, but similar beers, they kind of go together. So on one side, we have all the dark beers, and then all the high alcohol beers, and then the sour beers on a different, kind of on a league on their own, and then all the lagers or the wheat beers. So the grouping here really makes sense, even after dimensionality reduction. So the obvious application here is kind of planning for your next pint. But really, this is just about understanding the language. So word embeddings are a powerful tool to understand the language. And they will pick up all the different nuances of the language, all the cultural biases that I mentioned earlier in different data sets. And as a kind of an exercise, I also used it for a classification problem. So given a beer review, can you predict the exact beer style for this particular review? And it turns out word embeddings give you an improvement compared to traditional bag of words and, let's say, classic approaches. So just wrapping up, word embeddings are based on co-occurrences, and this is nothing new. So there are many other approaches based on co-occurrences. In particular, if you think, for example, LSA or LDA, this type of algorithms, they've been around for a while. And what happens with word embeddings, usually you have anyway a better representation. So word2vec tends to outperform LSA, LDA, and friends in many different tasks. And also there's an aspect of scalability. So word2vec is really an approach that scales to a much, much bigger vocabulary compared to LDA. So there's an efficiency aspect behind it. On one side, the model is based on co-occurrences, but there is no co-occurrence matrix in memory. So the vectors are learned as you go. The vectors are learned directly. Also, I mentioned the softmax function as kind of the core of the algorithm. And the softmax, if you remember, is normalized over all the vocabulary. So it has a complexity which is proportional to the size of the vocabulary V. So there's a trick also. I don't remember all the details by heart, but essentially you have a binary tree, and this will bring down the complexity to a logarithmic one. So with the hierarchical softmax, the complexity is proportional to the log of the size of the vocabulary. Then garbage in, garbage out. This is something fairly common in data mining, machine learning. So the idea is your pre-processing stages are still very important, and the business domain is particularly important. So your data are important. And I mentioned Google released the word vectors as part of the Word2Vec, and they're very useful because they kill the training time to 0 until they're not useful anymore. Why am I saying that? The thing is, these Word2Vec vectors, they've been trained on Google News. So it's a very specific kind of niche. So news, journalistic language, and maybe a little bit US-oriented. So for general purpose English, you can get started using the pre-trained vectors, but otherwise you should really train your own model. And in particular, if you have about 100,000 words in your document, in your data set, you can pick up some of this relationship and interesting similarities. And if you have 1 million words or more, definitely train your own model. 1 million words is a small data set anyway. Okay, so as a summary, if you've never seen word embeddings before, the first time you do vector arithmetics, it looks like magic. Really, it's just a very smart way of doing unsupervised learning to pick up on the notion of co-occurrences, distributional hypothesis, and so on. And if you don't care much about the theory, anyway, you can still benefit because GenSim, this Python library, makes your life really easy with an easy-to-use interface. And you can get started quite quickly. And I just want to mention a couple of people. Lev is a friend of mine who is involved in the development of GenSim, so we had a lot of conversation about word embeddings and GenSim itself. And this guy, Chris Moody, he has a lot of material on word embeddings, LDA, and this kind of text analytics approaches. There are a few videos of him. He has a nice way to describing complex concepts in a very accessible way. And my slides are online, so if you want to kind of read more, you have a few references as well. Okay, so I believe we have a few minutes for questions, but I'll be around anyway for the rest of the day if you want to talk about natural language processing and whatnot, and I'm fairly easy to find online. Thank you.
Thanks, Marco. That was a very interesting talk. Would you like to ask some questions?
Hi. Does the algorithm have any? Oh. Does the algorithm have any notion of the kind of grammatical structure? It looked as you were going through it, it was taking at and I. Does it look for verbs, nouns, and make use of some of that sentence structure?
Okay, yeah, good question. Is there any notion of grammar in the algorithms? The short answer is no. It's just based on co-occurrences. If your data set is large enough, you will end up picking up some of these aspects. So, for example, with the analogy Rome to Italy and Paris to France, you can do it also for singular to plural, male to female, and so on. You don't really know which one is a noun and which one is a verb. You don't have a notion of part of speech tagging and whatnot, but you still pick up a lot of these analogies and relationships, and they're not really labeled. So I told you before the relationship is capital of, but the algorithm doesn't know that. We know it after we analyze the data. So there's no explicit grammar, concept of grammar in the model, but a lot of these aspects are being picked up by the model if your data set is big enough. And it also depends on your pre-processing. So you can choose to do stop or removal, to do stemming, the usual kind of pre-processing steps for natural language processing. But if your data set is big enough, you can choose to avoid all the pre-processing and let the model pick up what's going on with the language. With the example with CVs and skills, we didn't have proper English. We didn't have a grammatical sentence. So the sentence for us was just a list of skills. It's not plain English. It's just a list. So yeah, you have many options there. You don't have grammar explicitly, but sometimes you can see it.
Hi there, thanks for your talk. Could you give an example of how you might use Word2Vec for supervised learning? So say if you wanted to classify a document into one of several categories.
Yes, Word2Vec for supervised learning. So you would have a first unsupervised step, which is learning the vectors, and then you use the vectors as features of your classification problem, for example. So the approach would be, rather than using a bag of words, so counting the words, you use a bag of vectors, if you want. So the vectors, after training this Word2Vec model, can be used by any other model later on. And it doesn't matter the application, really. It could be classification, it could be whatever.
Hi, I've got two questions. One is, basically, are word embeddings independent of the language you're analyzing? So can it infer the language and the relationships? And the second is on bias. So you've mentioned, obviously, that any data set will be biased because the language is. But how would you recommend sort of checking and testing whether there is, or how significant the bias is, or if it's problematic?
Okay, so about the language, the algorithm per se is language independent. So it's being used also for machine translation. So you can learn vectors in English on one side and learn vectors in Spanish, Italian, whatever, on the other side. And people notice these vectors, they are kind of similar. Maybe there's some rotation going on, whatever. But anyway, if your data sets are big enough, you end up with vectors that are fairly similar. I don't do much machine learning, so I'm not up to date with the latest literature, but there's a lot of paper about it. Language identification is one of those problems that is kind of 99% solved. So it's fairly easy to identify the language on one side without word embeddings, and then you learn the vectors depending on whatever language you have. And for the second question about bias, so there was recently a keynote at PyData Amsterdam about data ethics, and the video should be online already, PyData Amsterdam. And there are a few examples. So Catherine, who's the person who gave this keynote, also is suggesting a lot of references for this kind of biases. And for example, the vectors learned by, the vectors shared by Google, they're trained on this corpus of Google News. So they pick up on this particular kind of language. So you can imagine vectors for the word Mexicans, Google News, US. They're very close to the vectors for illegal immigrants. And then you also have a lot of other aspects, for example, vectors for programmer, minus vector for male, plus vector for female. You should end up in programmer again, like female programmer if you want. But this is not happening really. So the language will pick up on the biases or what are the most common works, jobs for female according to society or according to the data set anyway, and that's what was happening with the vectors as well. To mitigate the bias, again, I'm not really up to date with the latest literature, but there are a few approaches, and if you check out that keynote that I mentioned, there are a few references. It's something, sometimes it's difficult to spot So you don't know it until you know it. But there are definitely options to mitigate the problem.
Any last questions, Marco?
Just a quick question here. Are you aware of any publicly available corpus or vectors for very, very specific particular use cases, like, for example, legal or some special cultural thing? I mean, how do you look for those?
Yeah. So are you asking about the vectors? If they're being as far as I know, no. The vectors, the pre-trained vectors that are available are only the ones from Google, and they are trained on this Google News. You mentioned legal, which is one of the kind of hot topics in NLP now, and of course they are very, very jealous of their data, so nobody is sharing anything in these particular domains. I don't think there is anything available publicly because, of course, they have a lot data, have a lot of value, and then these particular models probably they also have a lot of value, so people don't want to share. I know the Linguistic Consortium, they have data sets that you can buy at a reasonable price if you are a company. But other than that, I'm not aware of any publicly available release of vectors, pre-trained vectors. I would be happy to be wrong in this case, but I don't know.
Great. Well, thanks again to Marco for giving an excellent talk.
Thank you.
And now it's time for lunch downstairs, which is being sponsored by Data Idols. And this afternoon's talks will start again at talk will be at 1:30. We'll be just talking about our sponsors a little bit before that. And there are lots of interesting talks on what data science is missing out. So I look forward to seeing you back this afternoon.